Hi guys, today we are looking at the last trigonometric function, tangent function, and we are going to look at how to graph it. And this one is going to look different from sine and cosine, and you'll see why here in a minute. So the sine and cosine functions get their values from the coordinates of a point on the graph. So you can see over here that this point on the unit circle is represented by x, y, which we know that x is cosine, y is sine. But the tangent of an angle gets its values from the coordinate of a point on a line tangent to the unit circle. So basically what it's saying is if I were to draw this theta line, continue on past the unit circle, it goes through that point, maybe it's, maybe this is 45 degrees, for example. So I draw this, I would get my point of radical 2 over 2, radical 2 over 2, but then I'm going to keep going through there, and I'm going to have a line that is tangent to the unit circle on the x-axis, and it's going to, the coordinates for this point are how we get tangent. It's over 1 because I've moved 1 in the x direction, and then this point right, the y-coordinate is the tangent of theta. But what we really do is we get, this is how we're getting tangent, of where it's intersecting, where the tangent line and the theta line intersect. So what we're going to see here is that if I look on this side of the unit circle and I graph these lines, extend all of these angles, I mean all of these thetas, we can see what happens to our tangent values. I would be saying, okay, I've got the point 1 and then tangent of pi over 3, 1 tangent pi over 4. And so we know what cosine of pi over 4 is and sine of pi over 4, but now we're going to look at the graph of tangent pi over 4. And this is the graph that we end up with. It kind of makes, it almost looks like a cubic function actually. The graph below shows one cycle of the tangent function. And it says since the period is pi, notice I'm going from negative pi over 2 to positive pi over 2. And so that is a distance of a total of pi. The asymptote that occurs at theta equals pi over 2. This is a vertical asymptote, repeats every pi units. So what that means is that if I were to continue this graph, I could add another pi, so that would make it 3 pi over 2. I would have another tangent, and then I would have another instance of that graph repeating. Now, it says use the graph of y equals tangent theta to find each value. Tangent of pi over 8. Well, let me look at this. This is pi over 2, and this is where you really, like, we have been doing work with fractions, but you really got to think about your fractions. Oops. So this is pi over 2. If I've got 1, 2, 3, 4 spaces between 0 and pi over 2, so that means that I'm going to divide this into fourths. So I'm going to start by dividing it in half. If I do half of 1/2, that's 1/4, and half of 1/4 is 1/8. So then that means that this would be 3/8. All right, so tangent of pi over 8. So I'm going to say, okay, I go over pi over 8, and what's the value at that point? Well, it's between 0 and 1. I'm going to say that it's about 1/2. It's probably a little less, but that's okay. Tangent of pi over 2. Well, if I go to pi over 2, that's where one of my vertical asymptotes is. So that means that here, the graph is not going to touch that vertical asymptote. That's kind of the definition of an asymptote. So here it would be undefined. What about when tangent is 0? Well, at 0, that's where the graph is crossing through the origin, so it's just a 0. Tangent of pi over 4. Well, let me go over here, follow that up, and that's at 1. So that's kind of how we're using the graph to find these values. Oops, sorry. There we go. Let's look at some properties. If we have this function, y equals tangent of A tangent B, theta, notice that B has to be greater than 0, just like before we do, and really A should not equal 0, just like before. But we have theta in radians, pi over b is the period of the function. That makes sense because here period was pi and we had tangent theta. Remember that this is a 1 here. Pi over 1 is just pi. So pi over b is the period. One cycle occurs in the interval from negative pi over 2b to pi over 2b. And there are vertical asymptotes at each end of the cycle. And so we're going to take a look at what that means. All right, identify the period and tell where two asymptotes occur, then sketch the graph in the interval from 0 to 2 pi. Well, for the period, before we've been using 2 pi over b, but now we're just using pi over b. So in this case it would be pi over 2. So what that means is that every distance of pi over 2, or every pi over 2 units, we have a vertical asymptote. And it says that we have one cycle occurs in the interval from here to here. So this is a good way to find your first asymptotes. We're going to do negative pi over 2 times 2 and positive pi over 2 times 2. Well, this would give me negative pi over 4. This would give me pi over 4. If I were to keep adding pi over 2, think about it this way. I'm adding pi over 2, and really all I'm doing is doing 1/4 plus 1/2. That would give me 3/4, or 3 pi over 4. So I'm going to label this 2 pi. I'm going to put my midpoint of pi. And then I'm going to go ahead and put pi over 2 and 3 pi over 2. These again are just the standard for like the special points that I think are helpful to put on there. But I need my vertical asymptote at pi over 4. So my asymptotes, I need to write this as an equation first of all. They go at x equals, I could say negative pi over 4, I could say pi over 4, and just keep adding pi over 2 each time. So 3 pi over 4, 5 pi over 4, could continue to 7 pi over 4. It says a minimum of 2 asymptotes. We're not really going to worry about the negative ones right now, but if you give me that equation, that would count as one of the asymptotes. So I need an asymptote at pi over 4 first. So that's halfway between 0 and pi over 2. Again, I'm thinking of this as a fraction. So between 0 and 1/2, halfway is 1/4. So there's 1, here's another, because I had 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, my tangent graph is going to, each one of the graphs is going to cross the theta axis exactly halfway between the two vertical asymptotes. So I had one here and one here. Halfway between was at 0. So here, halfway between negative pi over 4 and pi over 4 is at 0. Actually, let me do this in a different color. Halfway between these two would be at pi over 2. Halfway here would be pi, 3 pi over 2, 2 pi. And if you want to graph on the left, you can, but really all I need to see is from 0. So you can do that. And then we're going to go through here. I won't be too terribly picky on your graph. However, I should see that from the left to the right, it is constantly increasing. So it shouldn't look like that. It should look like that. Notice that even though the rate of increase slows down a bit, it still is increasing. So you could stop like this, and that would be a perfect graph if you gave that. I'm not like complimenting myself there, just to clarify. All right, so find the period. So that would be period over b, which is 1/2. So that means it's actually going to be 2 pi. Because remember, if I divide by a fraction, multiply by the reciprocal. Finding the equation of two asymptotes would be x equals negative pi over 2 times b and pi over positive pi over 2 times b. So this would give me x equals negative pi. 2 times 1/2 is just 1, so negative pi, positive pi, and then I'm adding 2 pi. So really, if I wanted to look at the positive side and see how many, where would my next asymptote be? It would be at 3 pi. And I think that's helpful. I can show you why in just a second. So we've got 2 pi, pi over 2, and 3 pi over 2. I'm going to put my first asymptote at pi, and then note, or x equals pi, excuse me. Notice that I don't have any other asymptotes to graph. I'm not graphing the negative. I'm not graphing all the way up to 3 pi, but this is where it's helpful. I need to know where the midpoint is, and so halfway between those is at 2 pi. So that means that it's going to go here. Halfway between these is at 0, so my midpoint is going to go there. And my graph is going to look something like this. That looks a little parabolic, but really what I'm doing is graphing it like this. And what we're not seeing is that it's going like that. We're just kind of stretching out the graph. So it's not really a parabola, it's just that it does kind of have a little bit of exponential qualities where it's increasing slower and then increasing faster, closer to the asymptote. All right. So the period here would be not 2 pi, sorry, pi over 4, which means that we would have pi times the reciprocal. So those are going to cancel. Now I have a case where I just have a whole number. I have 4. I'm going to calculate my asymptotes. Negative pi over 2 times b. And then positive pi over 2 times b. Well, these would simplify to 2, so I'm going to get negative 2 and positive 2, and my next asymptote would occur at 6 because I just add 4. Remember, this is how much I add to get to the next one, so if I wanted to find the next asymptote, it would be at 10. When you are telling me where the 2 asymptotes occur, please write the equation of the line. Write it as x equals negative 2, and it's okay if you want to list them with commas, that's fine. So since I have whole numbers, I'm going up to 2 pi, so I'm going to put this at 6, 3, I'm going to go ahead and just put 1.5, and 4.5, you can put 1, 2, 3, 4, 5, 6, that would also work. Actually, that would be better. Just change my mind. Since my asymptotes are at 2, I'll count 1, 2, 3, 4, 5, 6. That works. All right, so I have asymptotes at 2 and 6. Now, where do my midpoints occur? Midpoint here is 0. Midpoint here would be 4. So I'm going to have a point here, and it's going to go like this. Just like that. And that would be our tangent function. Technically, 2 pi means that I would go like this and start it, but then not really finish it. I'm not really worried about that. You can just end it at 6. That's okay. All right, that is not your homework, but your homework is in Google Classroom. So let me know if you have any questions, and I will be happy to help.